Hi everyone. I'm so sorry. So last Friday we missed one lecture. So today we are at lecture 8. We'll see how we can make it up. So we do have some break week scheduled down the road. So perhaps I can record one actual lecture during that break week so that we can try to stay on schedule. So sometimes my personal schedule becomes quite challenging. So I'm sorry for this just kind of delay of lecture 8. So today we are going to discuss some really important thing, and that is multiplication. So far we have essentially what we have been doing is just to review what you already learned from kindergarten to grade 4. Addition, subtraction. No, we are not talking about subtraction yet, but we will. But before we talk about subtraction, we will actually review and discuss multiplication. And it may look very strange, but this is actually what happened to rigorous math. In case you will learn some really advanced college math later, you will see that subtraction is really just another name for addition. But addition and multiplication, they are quite different. They are truly essential for any algebra. By algebra, we really mean we talk about a algebra because there are different types of algebras. And we can actually unify different algebras by something called abstract algebra. But that's too advanced down the road. So today we'll talk about multiplication. So far you have been very curious why we talk about all those arithmetical operations, which I'm sure you are very familiar with, in such a way that all the new terms, new concepts, new definitions, making things so complicated. Because what we are doing is not just to give a quick review of exactly what you learned in school math. Rather, we present arithmetics from a very rigorous and actually very modern theoretical perspective. That's why we took pain to first define what natural numbers are. The natural numbers, they could seem to come from nowhere, right? That's at least what you learned earlier in school. But the modern treatment of natural numbers is to maximize the range of natural numbers. And starting from there, we define what addition is. And now today, we will take one huge step further, define what multiplication is based on addition. But it may look quite advanced. Essentially, you have to understand and actually memorize this fact. Addition is nothing but repeated counting. Addition allows or enables accelerated counting. Multiplication, on the other hand, is nothing but repeated additions. And multiplication enables accelerated additions. And that's what we are going to discuss today. All exciting stuff. But before doing that, let's have a very quick review, because we cannot emphasize enough. We really need to instill those important and modern and the very rigorous concept about the very basic arithmetics. We want to instill those concepts upon you. Okay, so addition is really just repeated counting. We have already learned that. So we define 5 plus 3 as increment 3 times starting at 5. That's what we define 5 plus 3 means. And on the number line, you can clearly see that we start at 5, increment once, twice, 3 times, we arrive at 8. And we also talk about if we really want to add big numbers, we cannot count that many times, right? So what do we do? Well, we can use the clever method called vertical addition, because addition enables, by itself, addition is nothing but a restatement of counting. But because of the numbers we use are organized in such a way, decimal system, this very operation enables accelerated counting. And that is based on the fact that we are using a positional number system, like the Arabic Hindu numerical decimal system. We already saw that. We can do vertical addition like this. It's important to understand that when we do vertical addition, all we need to remember those facts is that how you can perform single digit addition. So from 1 plus 1, 1 plus 2, 1 plus 3, all the way to 1 plus 9, then 2 plus 2, 2 plus 3, all the way to 2 plus 9, and then 3 plus 3, and so on. We have in total 45 such facts. If you memorize all those facts, then that's all you need to know in order to perform any complicated addition. No matter how big the numbers are, all you need is just to remember the single digit addition. So don't take this as something trivial. It's very clever, and actually it's also very profound why we can do this. This is because of the associative and commutative laws of addition, and because of the decimal system we are using. Okay, so given those two, we can use this relatively small set of facts. 45 set of facts allows us to do any difficult big addition. In that sense, we say addition enables accelerated counting. So that when you have something like the 876 plus 948, you don't have to count 948 times from 876 to see what the result is. Okay? So you will see that those kind of ideas will also be extended from addition to multiplication. So, what if we need to perform this? We know addition is accelerated counting if we do it well. But is that acceleration fast enough? Now we want to do complicated additions, actually repeated additions. We want to add 948 copies of 257 together. So we will perform the addition operation 947 times. This number subtracting 1. So we will have to, if we don't know anything else, remember for now we have not defined what multiplication is. So we only know addition. Therefore, we have to perform this 947 times. There's no shortcut. Or you can, even worse, you can count 257 and then 257, do that, repeat that for 947 times. Of course, we know we don't need to do that because we have addition available, which is accelerate counting. But still, this is a huge problem, right? We don't want to do something like this repeatedly. So what do? Well, mathematicians discovered that we can have a new arithmetical operation, and that is multiplication. But how do we define multiplication? Remember, you learn all those addition rules, multiplication facts rules, and so on, vertical multiplication. But where did they come from? That's the thing. That's why we're taking a very rigorous approach to even elementary arithmetic. We want to have a clear and well-defined multiplication operation. So before doing that, you first want to review how we actually define addition, right? So this is a review of the definition of addition. Remember, right now we are only discussing for natural numbers, meaning from 0, 1, 2, all the way, all those positive numbers. So recall that we define addition in this way. We first define the first step. If you have a natural number m, we won't define what is m plus 1, because that's the quintessential increment operation which allow us to define natural number. Once we know what is m plus 1, then an arbitrary addition m plus n is defined through this m plus 1 effectively repeatedly. We define it m plus 1 plus 1 plus 1, do this n times, and then we get the definition of m plus 1. That's why we say addition is just counting with repeated counting forward. This is very important to recognize that the definition is very straightforward and very intuitive. Okay, but from this point on, how can we further define multiplication? Well, actually not too difficult. Because we want to accelerate these boring repeated additions, we define multiplication like this. Again, this is only of natural numbers, okay? So let m and n be any natural numbers, two natural numbers. Then this multiplication operation, of course we know this is called multiplication symbol, but this cross is the operation symbol, okay? Over m and n is defined as, we need to be very careful about here. We first want to define a zero case. So 0 times m, so that means that if m is 0, that's 0. So 0 times any other natural numbers, including 0 itself, n could be 0 itself, but if the first number times any such natural number, we define it to be 0. Let's be very clear. You think that, oh, 0 times anything is 0, but why? Why? Because we define it to be, okay? And this definition really follows our common sense. We will see that the first number here, m, is called the multiplier. And the second number in this m plus n, the n, is called the multiplicand. Okay? So this is just convention, which one is which. But generally, we define the first number m is the multiplier, and the second one is the multiplicand, or the number that is being multiplied. So essentially, This is that the multiplier is 0. So 0 copy of this number, it should be 0. Okay? Now, with this one, we further define the general case m times n or multiplies n. This is defined. We start at 0. We just add n because we already have the definition of addition, right? So we can perform m plus 0 plus n. Once we have that, we can perform another operation of plus n. And we repeat this m times. Okay? So you can see that multiplication is truly just defined to be repeated addition. Essentially, it's still accelerated counting. Think about it. Remember, addition is accelerated counting, and multiplication is just repeated addition. Therefore, it's a repeated counting. It's still counting. Okay? It's just turbocharged. Okay? So, multiplication is defined in this way. We start at 0, we add n m times. Okay? So, now, with this definition, how can we understand it on the number line? Well, as it turned out, oops, I don't know what happened. Yeah. Okay. Let's have an intuitive understanding of this one. Okay. So, we already know what is counting, right? If you have 0 plus m, you start at 0, you count it 1, 1, 2, 3, 4, until you get m. So this is m. Now, if you want to add another m, clearly you just continue to count forward, so that you just add, starting from m, you count another copy of m. So this is m plus 1, m plus 2, and so on, until you hit 2m. Right? So this is the second copy of the m. So until you add the final copy of m, this is m. So at this point, actually, I'm sorry, it should be n. We are counting, yeah, sometimes the multiplier and the multiplicand can be easily confused. So everything here should be labeled as m to n, and this is n copy, and this is n copy, and finally you add the last copy mn, and that's about it. Nothing really fancy, because we are just keep counting. One copy of n, you count n unit length, and adding another copy n, you count again another n unit lengths, and until you get the last one. That's about it. So that's what multiplication is visualized on the number line. Okay? Now, remember we have commutative properties or commutative law and associative law for addition. Okay, we were very careful to say, we did not say commutative law and associative law without any qualification. We say that for addition over natural numbers. As it turns out, multiplication also enjoy the analogous commutative and associative laws. And this is not a coincidence. Why is that? Because multiplication is essentially just addition, right? It's nothing but repeated addition. So if addition can enjoy commutative and associative laws, it's intuitively just natural multiplication should enjoy exactly the same law. And that's actually true. So we have those two propositions. Commutative law for multiplication over natural numbers and associative law for multiplication over natural numbers. And very similar to the same laws for addition. We just replace the addition operation with the multiplication operation. So for any two natural numbers m and n, m times n equals n times m. In the less abstract form, say essentially 3 times 5 equals 5 times 3. Okay? How do we understand this? Why this is true? Well, how did we interpret this on the number line for addition? Remember? Essentially, the commutative laws for addition is something like this. 3 plus 5 equals to 5 plus 3, right? How do we interpret it on the number line? So we start at 0. The first number is 3, so we have a 0, 3 line segment right here. Because it's a plus 5, so starting at 3, we counted forward 5 times to arrive at 8. And this is the second line segment. This is the first one. The second one is labeled as 3, 8. We use this simple notation to illustrate this is the second line segment. So 3 plus 5. The geometric interpretation of this law on the number line is nothing but if we swap the two line segments, essentially move this one to the left and move this one toward the right. We understand that the total length of this so-called concatenated or just seamlessly connected total line segment, the length should not change. And that's actually a big assumption. There's an implicit axiom for that. But it's intuitively very natural when you swap those two, reconnect them, the total length should be exactly the same. Therefore, this explains why 3 plus 5 equals to 5 plus 3. Okay, now with addition, we want to see 3 times 5 equal to 5 times 3. Why is that? Well, we do not have something as easy as the addition, but we can explain that. Okay, what is 3 times 5? You have 3 copies of 5, right? Economic together. So let's consider we start from 0. This is 0, so start from here. We have 5 as the first number 5. We can have another 5, and finally we have 3, 5, right? Why this is equal to 5 times 3? Well, imagine for the 5 line segment, this line segment 0 to 5, we have 5 unit 1, right? Let's just think about we color rows with different colors. So the first one, let's just say is yellow, the second one is orange, and the third one is green, and the fourth one is blue, and the fifth one is red. This is not red enough, so perhaps maybe that's as red as it can go. So this is the first copy of the 5. And then we will count another 5. So this must be essentially the same thing. We will repeat this 5 copies. The third one is green, so, and the fourth one is this orange, blue, okay, blue, and then finally red. This is the second 5, right? Well, the next 5, essentially the same thing. We just repeat that. So we will see that this gives us 3 sets of essentially the same 5 unit segment. Now we are adding them together. But because of the theorems we have started so far, we know this 15 essentially is the concatenation of those 15 unit segments. Now we can shuffle them, recombine them in any order we wanted. And essentially, that's what the commutative law and the associative law gave us combined. Remember theorem 1.6.3? We can add them in any order. Essentially the same thing here. So now we can regroup them in a different way. We can group all the colors in one group. So we can group all the yellow first. We put all the 3 yellows together. So we got 3 yellows. And then we group the orange together. 3 orange, now it's 6. And we can, next one is green. Obviously we have 3 greens. And then we have 3 blues. And finally, we have 3 red. Now you can see that the total length must still be the same because we did not do anything. We just rearranged the orders of those 15 unit segments, right? So clearly, the total length is still 15. But what is the arithmetical interpretation of this? This is nothing but 5 times 3 now, right? This is the first 3, the 3 yellow, the 3 orange, 3 green, and 3 blue, and 3 red. Therefore, 3 times 5 equals to 5 times 3. And this is the commutative law for multiplication. Okay, so now what is associative law for multiplication? Well, very analogous to addition. You have 3 numbers, you multiply them together. The default order, if we don't have any parentheses, it will be still the same as the left-hand side, which is 3 times 2 times 5. You perform 3 times 2 first. Use the output or the result from that operation as the input or the first operator or the first number, which in this case is the multiplier for the second multiplication. So 3 times 2 first, then times 5 equals 3 times 2 times 5. Okay, so can this be also intuitively explained on the number line? The answer is yes. Okay, although for consistency, we really want to see how to do this. Remember, this just repeated doing this. But there's a better way, also not really for consistency, because we use number line. This is always doable. But there's another way of thinking of how to explain this. For example, even for the commutative case, usually there's a great area exploitation. So let's just consider we have a rectangle. If 3 times 5 is something like this, okay? Depending on you want to use whether the length or the width as 3 or 5. It doesn't really matter. So this is nothing but 3 times 5 equals to 5 times 3. If you rotate this grid by 90 degrees, right? You get something like this. This can also explain why 3 times 5 is 5 times 3. But how about the associative law? Well, you can extend this model into a 3-dimensional case, right? Now, this is a rectangle. Now, we have a 3-dimensional case. Now, you can see that if this is L, you have L many numbers, and this is M. You have M many numbers, and the height is M. Okay? So you can say it doesn't really matter in which order you multiply the 3 numbers to get volume, right? Everybody have already learned a little bit about volume. Also, for completeness, we have not formally discussed any geometry yet. But assuming that you have some very basic understanding of the terms here, we have a 3D figure. This is a rectangular prism. So, or let's just say this is a block. Okay, so LMM. So this means that you have L times M times N. Doesn't matter which you group first. You still get the same volume. That's what the associative law is. Okay, so this can also be explained by the number line. Although it will be hard to just kind of illustrate the actual operation, but it can be done. You can imagine there are 3 numbers. We essentially add in another multiple of what we have here, right? Let's just call this whole group as a mix. But we can add another dimension, another multiplier, and we label each. Say we have 3 red, blue here, but we add a subscribe. Say this is the first type yellow, and a second type another yellow, something like a really not so yellow, but let's just say a really close color to this. But we still call them generally yellow. So we can recombine them and show, not prove, just illustrate how the associative law works for multiplication. But this model probably is much easier to understand. You can see that it doesn't matter how you multiply those numbers together, okay? So, things like that. All right. Now, we are ready to introduce a super important law for multiplication. But before doing that, we want to see its application first. And that is really what we have been just mentioning all the time. Multiplication is really just a fast counting or fast additions. So, just similar to the case where addition enables accelerated counting, multiplication enables accelerated additions. And we jump right to the most important algorithm which you're familiar with, but perhaps you don't like this very much. Too much computation, but this is something truly important. Remember earlier we saw that we can add any arbitrarily large addition, perform that operation, as long as we remember 45 simple single-digit addition facts. Similarly, we have exactly the same concept. If you memorize 45 multiplication facts, meaning single-digit multiplication, those facts, then you can perform any arbitrarily large multiplication operation. You can perform that just by hand. And this is very clever, very fast. But to see why this works, we have to learn another important arithmetical law. And this law, unlike the commutative and the associative laws, which are separated for addition and multiplication, this law called distributive law actually needs both addition and multiplication. It's actually called distribution over addition. Okay, but before see why we need that for this, let's just review how the vertical multiplication works. And I believe in school many of you did not learn this in a good way, and that is how to properly write the carry-on digits. Okay, so this is an extended illustration of all the carry-on non-digits are clearly labeled. And if you never learn this, this is a very good chance for you to strengthen your understanding of this. Look, we have this multiplication, right? 948 times 257. 948 times 257. Remember, this is called the multiplier. We need such terms to sometimes to avoid just referring to those numbers in the arbitrary way. We want to clearly give them a name. This is called multiplicand. Okay, multiplicand. So essentially, this is the number of copies, and this is the number that is being multiplied. All right. This means that this operation means that there are 948 copies of 257. Add them together. So how do we perform the vertical multiplication? Well, while you have done this for years, we need to carefully review what is going on here and have a solid, very clearly defined process. And I want to emphasize this is what you want to do in your homework, and write down the carry-on digits as what we will show next. So 7 times 8, that's 56. That's a 5 carry-on. Where to write it? You just write there. Why? Because you're going to put another digit here, and this should be small enough, and it just right at the top right corner of that new digit. Not too far away and not right above it, so that you clearly understand this carry-on will be aligned with this number place. Okay, the place value is for the tens place, so that you will not just confuse yourself. So 7 times 8, 56, we write a carry-on here. 4 times 7, that's 28. Now I need to add this carry-on. 28 plus 5, that's 33. So that's 33. There's another carry on to the hundredths place, so I write right there. It's not right above the next digit, but slightly right, but on the top. Okay? So the next one is 7 times 9. That's 63. Now I know there's a carrying here. So 63 plus 3, that's 66. The next one, because there's no further digit, I don't have to write the carry on. I can write it down directly. I don't need another carry on. Otherwise, it's too superficial. So the next, we're now performing 5 times this. So 5 times 8, that's 40. Write a carry on right here, 4. 5 times 4, 20, 24. I write down the 4, another carry on 2 to the thousandth place. So 5 times 9, that's 45 plus 2, 47. I don't need to write the carry on 4. I can write it down directly. That's 10,000th place. Now finally, the last 100 digit times 2, 48. So 2 times 8, that's 6. 6, that's 1, right? 16. That's a 1, that's a carry on. Don't forget a carry on. 2 times 4, that's 8. 8 plus 1, that's 9. No carrying in this case, that's good. 2 times 9, that's 18. 18, there's a carrying 1, but I don't need to write it. I just write it down directly. Now I have finished all the 3 steps. Now it's the time to perform addition now. So addition also may generate a carrying, so you still follow the same thing. So this is 6, 3 plus 0, that's 3. And now 4 plus 6, that's 10. 10 plus 6, that's 16. 16 does generate a carrying 1 here. So 6 plus 7 plus 9, I can combine the carrying 1 with 9, get 10. 10 plus 13, that's 23. So I have another carry 2 here. So 4, 2, 8. 8 plus 2, that's 10. 10 plus 4, that's 14. So there is a carrying 1. Now this one, I do need to write it because there is a digit there. So 1 plus 1, of course, that's 2. So finally, the answer for this complicated multiplication is this. You may think this is complicated, but think about the alternative. Without this, you have to repeatedly add 257 in a total of 947 times to the very first copy 257. This is nothing, right? This is super fast. Okay? Because this is 247 of 43,000 something. A huge number. If you count, you will literally spend a whole day to count this and more. Okay? So apparently multiplication is accelerated addition. But the simple fact here is that every step of the way, we don't need to memorize anything like, say, 48 times 57 or even 48 times 7. What is that? We don't need to remember anything for that. We don't need to memorize anything. All we need is to memorize the basic single-digit multiplication. And that is so-called multiplication table. Especially in China, we call 99乘法表, right? 9 by 9 multiplication table. Actually, that's a misnomer because of the commutative property we already saw. We just need to remember, say, 3 times 5, 5 times 3. We only need to memorize one of them. Therefore, we only need to memorize half of that table. So it's a triangular table. It's not a square table, okay? So, but why this theorem works, or this algorithm works, this is absolutely beautiful. Because by memorizing a very small set of facts, we can perform arbitrarily large multiplication, which otherwise would, it may take a whole day just to do that, but we can do this in 1 or 2 minutes at the most. But why? Well, again, 2 things. First, we are using the decimal positional number system, which if you recall, this number 948 is not arbitrary. The information has already been nicely organized for you. There's a 900 there, there's a 40 there, there's an 8 there. Because of the positional system, the total value, this is 948 in the base 10 sense, but within this base 10 system, it has been so nicely organized for you. That enables this algorithm. That's the very reason we can do this, the algorithm. But you will see, we also need the distributive law. Shortly, we'll see that. Same thing for the second number. So this number is also nicely organized. So when you do this, every step of the way, you are actually taking advantage of the fact that both numbers have been so nicely organized based on this base 10 positional value system. Without that fact, you just cannot execute this algorithm. Remember last time we said that if there's a base 1000 system, meaning that there are 1000 symbols, not just digits from 0 to 9. There are literally 1000 symbols in that numeral system. So 948, this number, this value in that system is just one symbol. Essentially, this multiplication in that just positional system would be something like this times whatever that is, 2 weird symbol. What is that? You actually have to memorize it. Just like you have to memorize the single digit multiplication table or those 45 multiplication facts. If this operation is in the base 1000 system, this becomes a basic single digit multiplication fact, and you have to memorize it. Forget about it. That's not going to work for anyone. Even Albert Einstein cannot do this. I promise. Okay, so enough. So how do we understand why this vertical multiplication algorithm works? It's because of the all-important distributive law. All right? So, what is distributive law for natural numbers? Well, actually, don't overthink about it. It's not that complicated. But this law does need both addition and multiplication. It's actually the only law, arithmetical law, that connects the two fundamental operations, addition and multiplication. Okay? Actually, when you learn higher algebra, you will see that, again, as I mentioned earlier, addition and multiplication are two basic essential operations in such algebra. So, what is distributive law? Three numbers, L, M, N. If L times M plus N, remember the parentheses change the orders of operations. So, in this expression on the left, you have to perform the addition first. You calculate what is the result of M plus N, get that result, then use L to multiply that, meaning L copies of such a result, you add them together. Well, this law says that you can distribute over addition so that essentially it becomes L multiplies M plus L plus N. Actually, this should be written as, on the right hand side, although this is true, but we want to emphasize the order of operations. So the parenthesis is optional, but if we add it, it will make it even clearer because multiplication is an operation that has precedence over addition, so without the parentheses, it's still the same thing, but we want to emphasize this by adding the parentheses anyway. So the left-hand side is L times m plus n. You can see that it can distribute over addition. So this equals to L times m plus L times n. Okay? How do we understand this on the number line? Actually, quite easy. Okay, think about this. What is m plus n? We already see m plus n, first step, is the combination or concatenation of two line segments. The first one is m. The second one is n. That's the length of the two line segments, right? So on the left-hand side, you first do this first. Then you multiply this by L. L, remember, is the multiplier. And effectively, assuming this is the new number, m plus n is the new number, that's this one. Whatever that number is, when you times that by L, by the definition of multiplication, now remember this is down, okay? M plus n is now down. It's just a number now. When we do L times it, according to our definition of multiplication, this is nothing but repeat this combined line segment L times, right? L times. Until you hit the last one, you get L copies of m plus n. But each copy can be actually considered m plus n. So if we use our coloring scheme like earlier, we can color all the m as yellow and all the n line segment as green. Then we will do almost exactly the same trick as earlier with the, oops, this should be green. So you can see that each m is, oh no, sorry, this one is still, this is green, okay. So, oops, it's a little bit clumsy here. Ooh. So you can see that we can repeat this process. All the m copies with the yellow and all the n side line segment with green. When we add them up, we can clearly combine or group all the yellows together first, right? So that way, you can clearly see that if we put all the yellow, all the n first, we group all the yellow first, and then group all the green line segment, which represent those n's together, the total length must still be the same, right? And this is exactly L times m, all the yellow line segments combined first, then plus all the green line segments combined second, then combine them together, okay? So that really shows L times m plus n equals to L times m plus L times n. And this is the all-important distributive law, which connects both addition and multiplication together. So very important to recognize that this is not a law for either addition or multiplication, but it's a law for both operations to work together. Okay, this is super important. All right, so with this now, example 3 times 2 plus 5 equals 3 times 2 plus 3 times 5. Okay. So you also need to pay attention to the rigor of the definition. We don't say distributive law is something like this. Of course, by the commutative property, this is also true, but as a definition matter, this is not the definition of distributive law. This is applying the commutative law on top of distributive law. Okay, so the distributive law is strictly defined like you put the addition into the second number being multiplied, which is actually called the multiplicand. The first number is the multiplier. Okay, it's not in this order. But because of the commutative law, this does not really matter. Now we are in the position to discuss why the distributive law is so important, right? We already mentioned that connecting the two operations and allowing many convenient and or clever manipulation on algebraic operations, and we'll see what that means. Okay, so this is the key for the vertical multiplication algorithm. We just saw, right? 948 times 257. We perform that vertical multiplication, blah, 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 blah. But why this works? Well, to understand this, we first need to understand a multi-digit times a single-digit operation. Okay, for example, let's just consider the second number, which is the multiplicand here. It's unit digit. Let's just say consider this one. How does this work? Well, this is, of course, we already did this in the overall procedure, but let's do it again anyway. So 7 times 8, that's 56. A carrying of 5. 4 times 7, 28, plus 5, 33. A carrying of 3. 7 times 9, 63. 66. That's it. This is still the vertical multiplication, but a special case where the second number is just one digit. But why does this work? Well, this is exactly because we have the distributive law. Let's recall that because of the positional number system, 948 is nothing but 900 plus 40 plus 8, right? So essentially, we break any decimal number according to its place values. Unit place, tens place, hundreds place, blah, blah, blah. We break that down into a format like this. Any number can be written this way, right? This is just how, the very reason we can do this is because of the positional decimal number system. In other words, this is the very meaning of what we write down something like 948. This is essentially the definition of this symbol. It means 900 plus 40 plus 8. It's just its definition. Okay, because of that, we are doing this, right? By the commutative law, we can swap this, right? And then we can distribute it by using the distributive law. Of course, if you will, you can swap all the three sub-multiplication together by using the commutative property again. Write down something like this. What I'm saying here is that also you don't have to write that to intermediate step. You can jump directly from here to here. But you need to mathematically, if you want to be a truly understanding and mathematical mind, you need to recognize that this is not distributive law itself, but this can be considered theorem. That is always true because it combines the commutative law and the distributive law. So from here to here, directly, always true. It's just that this itself per se is not distributive law. Okay, because like we said, order matters. It's very important to develop such mathematical thinking. Every step of the way, you need to be very rigorous, know exactly what you are doing and why. Okay, so now this is essentially distributive law, right? And that's exactly what we are doing here. Remember, we do 7 times 8. We got 56. That's where this guy came from. So essentially, we wrote a 56 here. Okay? Remember, 5 is in the 10th digit. But now next we do 7 times 4. And why that works? Essentially, what we are doing is 40 times 7. There's a hidden 0 there. We are doing in this diagonal way because effectively what we are doing is 40 times 7. But we know 0 is always bounded by 0. By the way, this is actually the associative law of multiplication because 40 times 7 essentially is 4 times 10 times 7. We can group 4 times 7 first. This equals 4 times 7 times 10 because this is the commutative law. We can swap 7 and 10, then swap back. This is all those things we have got a taste in when we work with addition, but essentially the same thing. We can change the order no matter what. So this is 28 times 10. So essentially, that's why we can do it this way. 4 times 7, that's 28. We just did not do anything with that, leave that blank. So remember, when we do the second digit, we start at this position, okay? We start at this position, pretend that nothing happened there. But that's where that 0, of course, in some system, the teachers may actually ask you to write down that 0 implicitly, but that's kind of just treating you like a toddler. You don't need to do that. Okay, so really what happened there when we times 4 times 7, we pretend this is the unit digit, but it's not because there's a hidden 0 there. So this is really effectively the 10th digit for the purpose of this arithmetical operation. So we just pretend this is the unit digit for 4 times 7. Well, in fact, the 10th place, that's why we need to add this carry from the unit digit. So when we do this every step of the way, when we do the third one, 7 times 9, that is effectively 900 times 7. Okay, so this is 6,300. So the final result is when we do this, we were effectively doing 7 times 8, that's 56. 4 times 7, that's 28, that's 280. And 7 times 9, that's effectively 6,300. So what we were doing here essentially is what we are doing here. We add rows together. You don't see 56 because there's a carry there, okay? So you don't see 280 because we already added the 5 to 28. That's where we got 33. Remember, that's a carrying 3 to the hundredth place. So effectively, we were doing this. We were just taking some shortcut to do some combination or addition just before the final addition. So we were doing all those along the way. That's why you see a 6 here, because this 33 will carry a 3 to this 3, so we get a final 6. So the point is that even the single-digit, multi-digit multiplication is a direct application of the distributive law. And that further explain when we do a full multiplication. So when we do 948 to 57, we do this in 3 steps. We pretend there's a single digit times 948, so we are doing this first. Okay, that's the first row. Okay, now we use 5 to do this. We pretend this is 948 times 5, but effectively it's times 50. Because remember, when we do the second row, we shifted it afterward. We pretend nothing here, but there's a hidden 0 there. That's where effectively we were multiplying with 50 instead of 5. But the same truth goes for the next digit. When we do 2 times 948, we were effectively doing 948 times 200. But we left further shifted by 1, so we left 2 empty space there, which are actually 0, 0. So that's rows to zeros. So what were we doing with this whole vertical algorithm? We are doing this. We are doing 948 times 7 plus 948 times 50 plus 948 times 200. That's exactly what it is. So essentially, you can easily see this is because we were using the distributive property to do this. 257 is written as 200 plus 50 plus 7. And we are distributing over this, over this, over this. So the full vertical multiplication algorithm is nothing but a repeated application of using distributive property. And the essence of this algorithm is that at the end of the day, everything will be stripped down to single-digit multiplication. Because of all those techniques, we can ignore the ending zeros. Anytime there's a 0 there, we just ignore that. But we implicitly include it when we do the vertical addition every step of the way. Okay? And one more reminder, the very reason you can ignore those trailing zeros is effectively because you were using the associative property for the multiplication. So this explains where all those vertical algorithms, why they work. Because of the 3 super important laws for them. Commutative property, associative property, and those apply to both addition and multiplication. And finally, we have distributive property. And this applies for addition plus multiplication together. Okay, I'll see you next time. Bye.